So we're going to use some resistors we've done before. We're going to set up our digital multimeter on the side to confirm our values. So I'll set this to, I think this first one should be, let's set it to here, 20 k ohm scale, and measure the resistors individually before construction. So I verify that I have something close to a 1 k ohm resistor for R1. R2 should be my 5.1 k ohm resistor, and then R3 should be my 2 k ohm resistor. So the measurements seem fairly close to my design, yes? So R1 again is intended to be the 1 kilo ohm resistor. And if we're measuring at 1 kilo ohm, let's go to the 2 kilo ohm scale. So I was at 20 kilo ohms, and at 20 kilo ohm scale, take a look at this. At 20 kilo ohm scale, I'm only showing 1.00. I want to get an extra digit of resolution in there. In fact, it's showing 0.99, which could be interpreted as 990 ohms, yeah? So the 20 k ohm scale is not giving me as much resolution as I would like. It is far in excess of 1,000. So what should I do? I should change the scale from 20K to go to 2K. And when I go to the 2K ohm scale, I will be able to achieve what we call greater resolution. In other words, I'll be able to see more digits on the display of my meter and give me something there. I got an extra digit. So instead of 0.99, I have a 0.992. So originally in the 20 k ohm scale, I would have said 990 ohms, but because I'm using a 2 k ohm scale, I have better resolution, higher accuracy. So instead of 990, I can call that out as 992 ohms. Everybody see that? Just by changing the scale, we're able to achieve higher resolution on our measurement. Now, the next one is 5.1 kilo. So can I measure 5.1 kilo on a 2 kilo ohm scale? No, there's no display because 5.1 kilo exceeds my 2 kilo ohm scale over here. So since it exceeds my 2 kilo ohm scale, the display won't show anything other than a 1 point, which means I've gone over the limit of the scale. So I should change this from 2 k ohm to read up to 20 k, and I will do so now. And I will go ahead and reattach across here to here. And when I go to measure, I expect something close to 5.1 kilo, and I end up with a 5.09 kilo ohms. Now, suppose my scale was adjusted from 20 k ohms up to 200 k. What do you think would happen if I go from 20 k ohm scale to 200 k ohm scale, measuring the same resistor? What do you think would happen on the display? Wei, what do you think would happen?
The 5 will go to the decimal place, I guess.
Okay, I would, that's very possible. Jacqueline, what do you think would happen if I change from the 20 k ohm scale to 200 k, measuring the same 5.1 kilo ohm resistor?
You would lose your 0.09 because
I would lose my
don't have enough space.
0.09. Yeah, I would not have enough space. I would lose a digit is what would happen, eh? Yeah, and then, yes, and so both of you are correct. It would become the 5 and the decimal point would shift, and I would lose the 0.08 or 0.09 portion of the display. Let's go ahead and see what happens. I'm going to do the one-hand technique of holding my probes in place, and then I will change from 20 k ohm to 200 k and see if that verifies our predictions. Lo and behold, guess what? My decimal point and the 5 shifted to the right, as Wei predicted, and as Jacqueline predicted, I lose my 0.08 or 0.09 resolution, and it rounds off to become 5.1 kilo. So for this particular resistor, which scale gives me the highest degree of accuracy? Brad, what do you think? Which scale gives me the highest degree of accuracy when I'm trying to measure the 5.1 kilo ohm resistor? Would it be the 2 k ohm scale, the 20 k ohm scale, or the 200 k ohm scale? Which one do you think, Brad?
I believe the 20 k ohms.
The 20 k ohm scale. Well, let's see. 200 k is here. I've got 5.1 digit. And if I go to the 20 k ohm scale, I've got 5 point with 2 digits. Could I possibly go to the 2K ohm scale, Brad?
You could, but it's not going to be as accurate as the 20K.
It's not going to be accurate at all. Why will it not be accurate at all? Because doesn't 5.1K exceed 2K?
Yeah.
So yeah, that's the reason. Yeah, so it wouldn't be accurate at all. It's not that it wouldn't be as accurate. It wouldn't be accurate at all. We wouldn't be able to see anything because at 2K, the 5.1 kilo ohm resistor is already higher than 2K, so we would see nothing. So the best resolution for this resistor would be at 20 kilo ohms. And the reason why I wanted to review this with you all is when you go to do your circuit builds, you want to make sure you have the right resistor measured and positioned in the correct place on your boards. Now I have got one more resistor to measure. I've got a 1 kilo ohm resistor here to measure. Which scale? Oh no, we already did the one. We did the one right over here. Yeah, we did the one. So this one's a 2 kilo ohm resistor. So as this is a 2 kilo ohm resistor, question goes to, hey, Yusuf, are you with us?
Can you hear me?
There you are. Yeah, we can hear you. Speak up a little closer to your speaker. But here's the question for you, Yusuf. The question is, if I'm trying to measure a 2 kilo ohm resistor in this third position, which scale will give me the highest degree of accuracy?
I would recommend using the 20K, right? You want it to be above.
Ah, so you want it to be just above the value we're going to measure. So if I go to 2K ohm, what would be the hazard if I try to go to a 2K ohm scale, and this is a 2K ohm resistor? The hazard is if this is slightly more than, if it happens to be slightly more than 2000, I wouldn't be able to measure it. It would be over limit. It would be a 1.0 something. Yes, but if I go here to 20K ohm, 20K ohms, you're right, Yusuf, 20K ohms would have been the prudent thing to do. And as it is the prudent thing to do at 20K, I come to discover, it's measuring 1.99, 1.98. So guess what? I could actually back this down to 2K ohms to get higher resolution, right? Because it will fit. This measurement is actually less than the 2K ohm limit of the scale position. So right now it's showing me 1.98. So if I switch this to 2K ohms scale and hold steady, I gain that third digit of information, which turns out to be a 1.981 kilo, yes? All right, so is this good review on how to make measurements of resistances along the way? All right, now I'm going to show you something else that's interesting in our circuit builds. So let me reiterate on the piece of paper what it is that we have in place. We have R1, we have R2, we have R3. R1 is planned to be 1 kilo ohm, and this is a 5.1 kilo ohm, and this guy over here is a 2 kilo ohm resistor. All right, so since those are in those positions and we've measured them individually, the idea here for this go around is to build them in parallel. Well, what does parallel mean? Parallel means that these resistors on one side have to meet at a common node, okay? On one side of these resistors, they have to meet at a common node. Do the lower leads of these resistors, and I'm going to come in a little closer, turn off the multimeter, save the battery. Okay, that's off. And I'm going to come in a little closer, right to here. Okay, I think that's good. And angle here and focus. Perfect. Wow, that is razor sharp. All right, so if you look at this very carefully, the bottom lead of this resistor is on row 25. 24 is here, 26 is here, and this wire happens to be covering up row 25. So the resistor is on tie point row 25, and this jumper wire is on row 25 coming over to my blue rail. So that's connected to the blue rail. Take a look at the bottom of the second resistor. The bottom of the second resistor happens to be on row 20. It's identified up here. You can see that's 20, 20, and it comes down here to 20. And the yellow wire happens to be covering up the label for 20 because you can see 19 on this side and 21 on this side. So is the bottom of the second resistor also connected to the common node with R1? The answer is yes, so far. And how about the bottom of R3? The bottom of R3 I have positioned on row 15 as identified up here. You can see 15 clearly, and it's 15 down here. And the number 15 is covered up by the yellow jumper wire. You can see 14 on one side and 16 on the other side. So does it look like the bottom of these three resistors, are in fact connected to a common point? Yes or no? Thumbs up if it's a yes. Okay, does that make them in parallel, yes or no? Not yet. It doesn't make them in parallel. What's required for them to be in parallel, according to the definition I've given you before, is that the leads on the other side of these components have to be connected to a different common node. So right now, take a look at the upper lead of R1. The upper lead of R1 is also on row 25. It comes up to here on these set of tie points. And remember, these tie points here are continuous with each other. The continuity pattern of the tie points in this position are perpendicular to your power rails. Did you hear that? The continuity pattern of these rows is perpendicular to your power rails. So I have 5 in continuity with each other. Does this point here that my green pen is pointing at, does this particular tie point have any continuity with my resistor R1, yes or no? No, it does not, because this is row 24. The resistors on row 25. Each one of these rows are numbered and they are completely separate entities of each other. Row 24 has nothing to do with row 25. All of these pins on row 25 have continuity with each other. Then that continuity is separated by the DIP support groove, and then these 5 on the other side of the resistor have continuity with each other. All right, that being said, this is just a reminder. So presently I happen to have R1 connected to row 25 tie points through a jumper wire to the red rail. In order for these two guys to be in parallel with each other, what must I do? I must connect the upper lead of this resistor, or the R2 resistor, to connect with the red bus rail, yeah? And so I can do so if I take a red jumper wire right here, a yellow jumper wire, and I go to position at row 20 there. Now do I have R1 and R2 in parallel with each other? And if I only have 2 resistors in parallel with each other, could I predict what those 2 resistors resistance total would calculate to be? So pull out your calculators, and the first calculation I'm going to ask you to do is going to be this. R1, and this double set of lines means parallel to R2 equals question mark. That is the question mark. And so what you do have, if I pull this up just a touch, there's a little more writing space here and see what's going on. Resharpen the focus, very nice. So it turns out that I happen to have 1 kilo ohm in parallel with 5.1 kilo ohms. And that's equal to sum total, just the pair of them by themselves. What does that calculate to be? How do we do this? Well, remember, we can do this a couple of ways. We can certainly do this using reciprocal formula. So reciprocal formula. So reciprocal formula is my RT will be equal to 1 over R1 plus 1 over R2. You can always rely on the reciprocal formula for 2, 3, 4, or as many resistors as you wish. So how do I key this into the calculator, do you recall? The calculator key sequence, and you should have had plenty of practice on that between Monday's meeting and now. If you haven't had practice, now is the time to practice. So here we go. This would be 1 kilo, so 1 exponent 3. Okay, so you have to hit the exponent key, 3, so that gives you kilo. Then what's the next button push that we're going to use, Robert? What's the next button push after keying in the kilo? You have to do what?
-1.
Excellent. We're going to hit the X-1 button. Okay, so we have taken the 1 kilo, we've hit the X-1, that's given us our first fraction of the denominator. What's the next step in the denominator? Is we're going to hit what key, class? The addition button. So I'm going to hit the addition button. And now we're going to reciprocate the second value. So the second value, Brad, what am I going to enter for my second value for this? Brad?
The second value will be 5.1 kilo. So
And how do I enter kilo in my calculator?
kilo would be the exponent 3.
Correct. It would be exponent 3. What would happen after I key in 5.1 kilo? What's the next step I should do?
The X-1, the reciprocal.
Correct. So we will do the X-1, and we have now taken the first reciprocal, added it to the second reciprocal. What should be my key at this point, Jacqueline? Do I do another add? What goes here?
Equals.
Equals. So everybody should hit equals. Are we done with this at this point, or is there another step yet to do? Weiji? Microphone? Weiji?
We hit the reciprocal key again.
We hit the reciprocal key again. So here we go. We hit the reciprocal key again, and then followed by equals. So if you take a look at this, my friends, that keystroke sequence that I've just written out is this formula spelled out. We had the 1 kilo, and then we hit reciprocal. Then we added it to 5.1 kilo and reciprocated. Then we hit equals to take care of the entire denominator. Once we've hit equal to take care of the entire denominator, we have to hit reciprocal equals one more time because everything in the denominator has to be divided into 1. So the end result, let's see, Robert, you're up. What's the calculated end result?
836.06.
836.06 what? Apples, oranges, what are my units for resistance? Robert?
Oh, sorry, my connection's bad. It was ohms.
Ohms, okay, thank you, ohms. All right, so let's go ahead, and how many people agree?
You guys want to round it?
Uh-oh, let's take a look. Let's take a look. Let's go ahead and take a look on the calculator. Let's turn on my calculator, and let's go ahead and key this in as we have proposed. So I will take, and let me move this out of the glare of the overhead lights. So clear, so I will take 1 exponent 3, and I'm going to hit reciprocal key, and I'm going to hit add 5.1 exponent 3, hit reciprocal, and then hit equals, hit reciprocal, and then hit equals, and then hit my engineering button. And engineering, so if you take a look at the display and you take a look at the proposed answer, what was one thing that we needed to do in the calculated answer versus what we write down on paper? What do you see here? 836.06, what's my third digit though? Do you see 0.065? What does this third digit tell you how you need to round that second digit after the decimal point, remember? So anytime that third digit is 0 to 4, you leave this alone. Anytime it's 5 and up, you round up. And since this is a 5, we have to round up the 0.06 to become what? So scratch this guy out. So we were off by 100th. That's okay. We're pretty close. This is all good practice. 836.07 ohms. Is that correct? Is everybody happy with that calculation and understand how it should be rounded off? Yeah? All right. Now, since I have two resistors wired up in parallel, and I have a predicted result of 836.07 ohms, as verified by my calculator, now I'm going to bring in the multimeter. And let's go ahead and measure this pair and see how we do. Now, if we're expecting 836.07 ohms, which scale should I select? The question goes to Brad. It's your turn now, Brad. Which scale should I select in order to read this 836.07 ohms?
The 2K?
2K. I wouldn't go 200, you're correct, because 200 is less than this. So this exceeding 200 will cause an over limit display. Let's go ahead and see that. I'm going to put this on 200, and I expect an over limit display if I try to measure these guys in parallel. Now, to measure these guys in parallel, I've got two resistors in parallel. I'm going to put a lead at the top. I'm going to put a lead at the bottom. And because these guys are in parallel, wow, yes, I have exceeded that particular scale. 836 cannot be measured on 200 ohms. So I will change from 200 ohms to 2K ohms, as Brad suggested. And then if I go here at the 2K ohm scale, let's see what happens. I'm at the top at the red bus rail. I'm at the bottom on the black bus rail. And lo and behold, I end up with 800 and, well, it's a 0.830, what? 0.830 kilo, yeah? Does everybody see that my scale is in kilo? And it's a 0.830 kilo. Well, how do you interpret that to become 830 ohms? You can very easily do this. It's 0.83 on a 2K ohm scale. So you could, until you feel comfortable, you could do this. 0.83, so there's 0.83, and kilo is exponent 3. Is that right? Did I key in 0.83 kilo on my display, which is what came up on the multimeter? If I hit equals and then hit engineering, does the calculator automatically shift to give me proper engineering notation, which means the appropriate power of 10? It's not a multiple of 3. This is just straight ohms, 830 ohms, which is what I measure between here and here. Everybody see my 830 ohms? 831, 830, right there. Okay. Now, interesting thing about parallel is this. I can move my black probe to the bottom of the resistor, right here, and still show my 830 ohms, yes? So whether I have my black probe at the bottom of the resistor, or whether I have my black probe on the blue rail, it's still 830. How about if I move my black probe to here? Still 830, yes? How about if I move my black probe to the bottom of R3? Now, R3 is not even part of the parallel sequence. What do you expect for me to measure if I put the black probe at the bottom of R3? This is a prediction question. At the bottom of R3, what do you think I should measure, Jacqueline?
Nothing. It's not connected.
R3 is not connected, for sure. And we may or may not measure nothing or something. Wei Ji, what do you think?
800 something, the same you measure.
So you think we should measure something. Jacqueline says we should measure nothing because it's not connected. Well, let's find out. And let me explain why we end up with the value that we do. So we already said over here, at the bottom of R1, we had 830 ohms. Right there. At the bottom of R2, we have 830 ohms. At the bottom of R3, we have 830 ohms. Why do we have 830 ohms at the bottom of R3 when R3 is not connected? Because the entire blue rail is 1 point. All of the blue rail is 1 point. Whether I put the black probe here, whether I put the black probe here or the black probe here, all of these points are connected with each other. It doesn't matter that R3 is not part of the circuit. What does matter is these points on the blue rail are all the same. So whether I put my probe, my black probe, here or here or here or here, I'm still going to measure 830 because all of these bottom leads are connected, even to the bottom of R3, even though the bottom of R3 is not hooked up to the upper part of the other two resistors. It's still, the bottom of R3 is still connected to the bottom of the other resistors. They are one large continuous point with each other on the bottom. So whether I connect here, the bottom of R3 physically, I get my 830. Whether I connect here on the blue rail, I get my 830. Whether I connect to the bottom of R2, I get my 830. The bottom of the jumper at the blue rail, 830. The bottom of this resistor, 830. And the bottom right over here, 830. Even if I go to the black jumper wire right over here, it's still connected to the blue rail. I'm going to show 830. Okay? So what I'm measuring is the resistances, the total resistance of these two guys in parallel with each other, and all of these connection points with my black probe down here are all going to give us the total resistance for just these two in parallel. So this is a learning experience. That's why some of the questions that I throw out there are leading questions. Some of them will lead you to a supposition that may turn out to be false after we do some explanation. And hopefully you can appreciate why hooking up to the bottom of R3 still allows us to measure 830 ohms, because the bottom of R3 is continuous with the bottom of R2 is continuous with the bottom of R1, even though the top of R3 is not connected to anything. Okay. All right, so the next exercise I'm going to do is I'm going to put two other resistors in parallel. I'm going to put this jumper wire from here to make, right here. So in doing so, by moving the upper jumper wire in this fashion, I now have a jumper wire from red rail to row 25 and row 15. So what kind of an arrangement do I have between resistors at the present? What do I have between resistors at, I'm sorry, I apologize for jostling the camera around. I will get this organized. There we go, focused. So what we happen to have now is R1 has what relationship to the other two resistors? Who can call out what their relationship is? Yusuf, can you call up what relationship between which resistors I have rewired on my board?
Oh, R1 is parallel to R3?
Okay, interesting. How many people agree that my R1, because I moved my jumper wire from here to here now, is physically in parallel with R3? Give me a thumbs up if you agree to that. Very good. And that is true. My R1 is in parallel with R3. The top of these two resistors are connected to the red rail. The bottom of these two resistors connected to the blue rail. R2 is hanging. The top is not connected. The bottom's connected, but the top is not connected. So it's physically, it has no electronic relationship with these two. So what is my value for R1? The value for R1 was 1 kilo ohm, yes? And the value of R3 was 2 kilo ohms. So I now have 1 kilo ohm parallel with 2 kilo ohms. And the question is, what is my R total? So that being said, let's go ahead and use our reciprocal calculation again. And if we're going to use our reciprocal calculation, question goes to Wei G. How do I set up my calculator keystroke sequence here? Do I write down for our classmates to follow, please?
So 1 and then EXP.
1 EXP,
3
3 for the 1 kilo. Then what do I need to do with that?
reciprocal key.
I'm going to hit my reciprocal key, x negative 1, followed by what?
Plus
Hit a plus.
2
And then what do I do? 2
EXP
EXP
3
3. what?
reciprocal key,
Hit the reciprocal key, x negative 1,
then equal.
then equals. Okay. Am I done?
And then hit the reciprocal key again
Hit the reciprocal key
and equals.
again and hit equals. So what you're proposing in this keystroke sequence is this formula, RT is equal to 1 over R1 in parallel with 1 over R3. And I didn't mean to write down parallel, actually meant to write down plus. So, sorry, there's a plus in here, okay? They are in parallel, but that's a plus. So what he's done the 1 kilo and reciprocated it, plus, right here's the plus, then 2 kilo, which is this guy, and reciprocate it, and then hit equals to finish calculating the denominator, and then we have to reciprocate it one more time and hit equals. So as I've been talking this, you all should have been calculating this. Don't sit there admiring the ink on my papers. Oh, okay, now I should pick up the calculator and now I should punch it in. Yes, you're so attentive, I commend you all. But let's go ahead and do this calculation. So Rodrigo, when we do this calculation sequence, my friend, what is it that you propose the answer for these two guys in parallel to be?
666.67 ohms.
666.67 ohms is the prediction. How many people give a thumbs up and agree with that value? Raise your hands or give us a thumbs up. Okay, Rodrigo, it's a good feeling when your classmates give you a thumbs up, which is great. And let's go ahead and confirm that, because if anybody didn't get that, let's go ahead and confirm that on our calculators. And so we will clear and we will hit 1 exponent 3 and we hit the reciprocal key and we're going to hit plus, and then 2 exponent 3 and hit the reciprocal key, hit equals, hit reciprocal, hit equals again. And since we end up with a 10 power, something other than 10 power multiple of 3, you hit the engineering key, lo and behold, guess what? 666.66 or 666.67. Everybody understands to round, correct? That third digit is a 6. It tells us we have to round that 0.66 to become 0.67 after the decimal point, which is what was predicted here, yes? All right, now that being said, we now have a target. Remember, you never do any measurements unless you have a target calculation to compare it against. So here is the circuit back in the picture, and I will go to an appropriate scale. So the question is, what is my appropriate scale in order to read this? Question goes to Robert. Which scale of ohms should I adjust the multimeter to properly measure this value that we've calculated?
2K?
2 kilo, yeah, because 200 is too small, and the next one up would be 2 kilo. So let's go to 2 kilo. We are now at 2 kilo ohm scale. Right, and let's go ahead and make the measurement. Red probe here, and black probe at the here. And we expect 666.67. Whoa, look at this. 661 ohms. Pretty good, yes? Is that pretty close to our 667? Pretty darn close in the real world, because you got to remember, it's not going to be exact. Why? Why is the measurement not going to be exact, spot on with our calculations? Question goes to Jacqueline. Why?
Because the resistors have tolerance values.
Yes, the resistors have tolerance, which means there is going to be some expected margin of error. Okay, and 661, pretty darn close. I'm happy with that. Now, where's my red probe? Where's my black probe? The red probe is on the red rail. The black probe is on the dark blue rail. Suppose I change my red probe to go physically over to the top of R3 right here. Do I expect the same measurement? Do I get the same measurement? Yes, I do, 661. Does it matter where my red probe is as long as I am somewhere on the red rail? Doesn't matter. How about this? Suppose I move my red probe from the red rail to the bottom of this jumper. What do you think I'm going to measure for our total if I go from this side of the jumper to this side of the jumper? What is your prediction of what I expect to measure if I move my red probe from here? Now, again, I'll show this to you. Red probe here shows that we have a measurement of 660, come on, hold on. Squeeze, 661 ohms, yes? So what do you predict would happen if I move my red probe to the bottom of the yellow jumper? So that question goes to Wei Ji, you're up. What do you think?
The same amount.
The same? Who agrees that it should be the same? Who's not sure what it would be? Give me a wave if you're not sure. Here you go. If you're not sure, it's okay, because this is part of our learning experience. So check this out. We had the red probe up here on the red rail, and we confirmed between the red rail and the blue rail 661 ohms, if I hold this steady. It's okay if it changes slightly, 662, 661, all right. And we said, I'm going to move the red probe from the red rail to the bottom of this jumper wire. And I'll tell you right now, it should be the same. And the reason why it should be the same is that jumper wire is nothing but a piece of wire. Means there's no ohms in here of any significance. That means whichever end of that wire I measure, it's physically connected to the same point. So whether I have my red probe on this side of the jumper to give me 661 in a moment. Hello, if I squeeze tight, right there. And whether I go to here, 661, watch this. 661, yeah, at the bottom of the jumper. Because the jumper is nothing more than a continuous piece of wire. We expect there to be no difference whether I put the red probe right at the red rail or whether I put the red probe at the bottom of the jumper wire. Let me ask you this question. This question goes to Yusuf. Yusuf, now it's your turn. What do you predict if I take my red probe and instead of measuring here at the red rail, instead of measuring here at the bottom of the yellow jumper, suppose I put my red probe right at the metal lead at the top of R1. What do you think we're going to measure, Yusuf?
We're going to get the same value again.
We're going to get the same value again. Why do you think we're going to get the same value?
Because it's a series circuit. We're testing the resistance of the entire circuit.
Mm-hmm. Okay, we're testing this. We're testing the resistance of the entire circuit. Don't use the word series, because it might lead some of our classmates. This is a parallel relationship between R1 and R3. Okay. But I think the words that you're looking for are this. We expect them to be the same, and let's verify if it is the same. Press and hold, steady, stab. And does it still hover 662 or does it go to 660? Okay, it does eventually go to 661. Everybody see that? How about that? And so the reason why we expect no change is because we have a continuous path of continuity between this wire, all of the wires underneath these tie points, all the way to the bottom of this jumper, and a continuous path all the way up to the red rail. So whether I measure at the top of this jumper, or the bottom of this jumper, right there, or the top of the resistor, it is the red probe is measuring exactly the same point electronically, okay? So I wanted to show you that because parallel circuits are interesting in that they allow you to make measurements of parallel in multiple places. Now, what would happen, and I think we've done this before, if I have the red probe here, anywhere along the red probe, we expect RT, right? Because the two resistors are hooked up to the red rail. What do you think would happen for my ohms if I move my red probe to the bottom of this yellow jumper? What do you think we would measure if I move my red probe from the top of the jumper to the bottom of this yellow jumper? Question goes to Brad. What do you think would happen? Would the value be different? Would it be higher? Would it be lower? Would it be the same? What do you think would happen?
I would think it would be the same.
You think it would be the same, and the reason why you think it would be the same should be verbalized this way, okay? What's really important is we want to make sure we verbalize that we're comfortable with verbalizing. You want to be comfortable with explaining to your middle school cousin what you understand, and the more you verbalize, the more confident you will be in this new language called electronics. So Brad says we should have the same measurement at the bottom of the jumper wire, and we're going to confirm that because we should. So if I press and hold firmly, do I have my original 661 ohms? And the answer to that is yes. Now, how do we explain that? We explain that this way. We expect the voltage at the bottom of the jumper wire to be the same as the voltage at the top of the jumper wire. Why? Because we lose no voltage across that wire. That wire has 0 ohms. That wire will lose 0 voltage. So whatever I measure at the top of this wire should be the same that I measure at the bottom of the wire, 661. That's how we need to verbalize this. And you can play this recording over and over again to listen to the verbalization, but you all want to get used to speaking the verbalization this way. Now the next question will go to, let's see, Yusuf, it'll be your turn. What do you expect for me to measure if I put my red probe at the top of R3?
That's going to be the same again.
Which is what value do you think?
661.
Let's go ahead and put it here. 660, let me hold steady. I end up with my 661, yes? Huh. Now I'm going to move my black probe. I'm going to move my black probe. I'm going to put my black probe right at the bottom of R3. If I put my black probe at the bottom of R3, what do you think we're going to measure if I have my red probe at the top of R3 and my black probe at the bottom of R3? Jacqueline, what do you think?
Same thing.
Which should be what?
661 ohms.
661 ohms. I'm not going to measure just this 2K ohm resistor by itself, even though I'm hooking up across it singularly. Anybody? Rodrigo, what do you think? Will I get the 661 ohms again, or will I actually measure 2K ohms because I'm physically right across the 2K ohms?
You'll measure 2K ohms.
Okay, we have 1 vote for 661, 1 vote for 2K ohms. Well, here's the thing. Let's go ahead and break the tie. Ready? 1, 2, 3. Guess what? I end up with my, hold steady, see if it bounces to, yeah, there we go, 661 ohms, yes? Huh. Even though I'm hooked up across the 2K ohm resistor itself, I'm measuring the 2K ohm in parallel with the 1K ohm. Why? Because isn't the top of the 2K ohm resistor still hooked up to the top of the 1K. They're still connected, right? And take a look at the bottom of the 2K ohm resistor. Isn't the bottom of the 2K ohm resistor still physically connected to the bottom of the 1K ohm resistor? They're still connected. So even though my probes are across a single resistor, because they are connected to each other, the 2K to the 1K ohm, I'm going to measure their parallel relationship to each other, which ends up to be 661 ohms if I press and hold this steady right there. Okay, so is this a new learning experience for more of you? Okay, just because I'm hooked up across the 2K ohm resistor by itself, it is not by itself. It is still electrically connected to the 1K. Now suppose I do this. Suppose I hold this in place. I get my 661, right? And suppose I go to yank a jumper wire. If I go to yank this jumper wire at the top of R1, what do you predict would happen? And the question goes to Wei Ji. What do you think would happen if I yank this yellow jumper wire right now? Because right now I'm measuring across R3, the 2 kilo ohm resistor, which is in parallel with the 1 kilo ohm resistor. I'm going to leave my red probes here, leave the multimeter on. What do you think would happen if I yank this yellow jumper wire? Wei Ji.
It go back to 2K ohms.
Okay, that's an opinion. How many people would agree it should go back to 2K ohms once I pull this yellow jumper wire? Raise your hands. How many people have a different opinion? What would happen? Yes, what do you think would happen? Jacqueline, you had your hand raised?
Oh, sorry, in agreement.
Oh, you are in agreement. Okay, you think that we should we should only see 2K ohms. How many people aren't sure what would happen? Give me a raise of hands. Okay, if I go to yank this guy out, this jumper wire, won't I destroy, no, let me move my hands back, I'm sorry. Won't I destroy the connection between R1 and the red rail? If I remove this connection between R1 and the red rail, R1 is no longer hooked up to the red rail. The only thing I have is R3. That's the only thing that's left. So I can only display, this multimeter can only display the singular resistance that is there. Watch this. I'm going to yank this guy up. And does it go back to my just under 2K ohms that I started off with much earlier? And this is what we should expect, because take a look at the top of R1. The top of R1 is floating. There's no connection. Take a look at the top of R2. It's floating. There's no connection. So these probes, the red probe and the black probe, can only read the singular resistor that is left. Okay? These good lessons for you so far in parallel circuits. Lots more to learn about parallel circuits. Okay. Now, the next thing that I'm going to do is the third combination. We've already done a 1 and a 3. We've done a 1 and a 2. So what we haven't done yet is a 2 and 3. So I'm going to go row 20 to the red rail, like that. Okay, so look at this very carefully. Study that. I get another piece of paper. And see if you can tell me what you expect the electrical relationship to be between these components and what I should be writing down for them. So the question goes to, let's take a look. If Roberto had come back on. Roberto, okay, so given this connection, R1 is 1K, R2 is 5.1, R3 is 2 kilo ohms, and now I've moved the jumper wire in this fashion. What electrical relationship do I have between the resistors? What I would write down for RT. RT is equal to what? What do you see here?
So R2 and R3 are parallel.
R2 is in parallel with R3. Does everybody see how we write that?
Can you hear
So
me?
R2.
Sure.
I'm sorry? What was the comment? I didn't hear that.
Connection is
Oh,
accurate.
we hear you fine. Yeah, you're coming in loud and clear. Yeah, Yeah.
Thank you.
Now the microphone is working beautifully. All right. So what we have, and Roberto's correct, we have R2 that's in parallel with R3. And the value for R2 was we had a 5.1 kilo ohm resistor in parallel with R3, which is 2 kilo ohms. And we need to determine what R total is equal to. So according to our reciprocal formula, RT is equal to 1 over R2 plus 1 over R3. So what we happen to have now would be R total is equal to 1 over 5.1 kilo ohms plus 1 over 2 kilo ohms. So this is how we set up the written formula, which is, and the name for this formula is reciprocal formula. So we take the 5.1, we have to reciprocate this. We have to add it to 2 kilo. We have to reciprocate that. We hit equals in order to calculate the denominator. Then we hit reciprocal one more time to divide it back into 1 and hit equals one more time. So the keystroke sequence, as I'm going to ask you to read out to me, keystroke sequence, I will go ahead and ask, Yusuf, can you give us the keystroke sequence for RT, please?
Okay. 5.1 exponent 10 to the third.
Exponent 3, okay.
Reciprocal
Reciprocal, x negative 1.
plus
And I have a plus key, then
2 exponent
2.
3
Exponent 3
reciprocaled
and reciprocal x negative 1
equals,
equals,
and then reciprocal again.
and hit reciprocal x negative 1.
You want
Are
the
we
answer?
done? No, are we done? Is this the last key
Equal
button I
again.
push?
Equal again.
I have to have equals in here, okay?
All right.
Okay, so we have this keystroke sequence, and Yusuf, what is your prediction?
1.44 kilo ohms.
1.44 kilo ohms. How many people agree? Give us a thumbs up. If you've done this on your calculator and feel comfortable, is the rounding correct? Everybody's happy? Okay, we now have a target. Remember, you can't measure anything unless you have a target calculation. So we hope that when we go to measure this, we will have 1.44 kilo ohms. That being said, all right, so the question, Brad, what scale am I going to set this on?
2K ohms?
Okay, 200 won't work because this is above 200. So 2K would be just above this, which would be fine. So we'll leave it on 2K. And I'll go ahead and take my probes and go to the top and go to the bottom. And lo and behold, we end up with, on my board anyway, not 1.44K, but 1.426 kilo. Again, because we have tolerance, that's pretty darn good. Now, how about if I put my black probe here? 1.426. How about if I put my black probe physically at the bottom lead of R3? 1.426. How about if I put my black probe at the bottom of R2? 1.426. How about I put my black probe at the top of the jumper wire right here? 1.426. How about the top of this jumper wire? 1.426. How about if I take my red probe and I put my red probe at the bottom of this jumper wire? 1.426. How about the top of this resistor? 1.426. How about if I put my probes right across the middle resistor? The middle resistor is a 5.1. So if I hook up directly across that middle resistor, what am I going to measure on the display of my calculator? Rodrigo, what do you think?
It's going to be the same.
Same as what?
1.46.
No, I
ohms.
had a 1.426. So even though my probes are across a single 5.1 K ohm resistor, I'm not going to measure 5.1 K, is what you're saying.
Yes.
Good, I like that. Commit. You got to commit, which is good. All right, so yes. All right, guess what? He's right. 1.42, if I hold it steady, 1.426. Even though I'm across a singular resistor, isn't the black probe still physically connected to the bottom of R3? Yes. So it doesn't matter I'm across just the singular resistor. This resistor still is in parallel on the top and the bottom with R3. Okay? I've got another thought question for you. I'm going to leave my red probe here. Suppose I take my black probe and I now go to the bottom of R3's jumper wire to the blue rail. What do I expect to measure here with my black probe at the bottom of this jumper wire? Question goes to Jacqueline.
1.426 ohms.
I'm not going to measure nothing because this resistor is floating.
No, because it's all connected, the blue bus.
I like that verbalization. Did everybody hear the verbalization? The verbalization is no, we don't expect it to measure nothing. We expect it to measure something, and that something was the value we measured before, which is 1.426, because all of the blue bus is connected. Let's test this. Boom. 1.426. Isn't that marvelous? How about that? It's really nice feeling when your predictions are verified and validated by your measurements, eh? But your measurements are meaningless unless you have a target value. And yes, Jacqueline said we expect 1.426, and we got 1.426. How about if I move my black probe from where it is? Suppose I put my black probe to the bottom of R1. Now, to the top of R1's floating, but suppose I put my black probe to the bottom of R1. What do I expect for the multimeter to measure if I put my black probe to here? Question goes to, let's take a look. Wei Ji, what do you think? Black probe to here. What do you think?
1.426.
Oh, why?
Because they're still connected.
Because the bottom of the resistors are still connected, huh? Let's see. 1.426. Isn't that marvelous? Isn't that great? All right, so far so good. Okay, now I'm going to hook all three of them together. So now we will have all three right there. They're connected at the top. This is on row 15, row 20, row 25 at the top. This is on row 15, row 20, row 25 on the bottom. All connected to the red rail on top, all connected to the blue rail on the bottom. Guess what I'm going to have you all calculate now? R total. So let's go ahead and write this up for R total. So RT now is made up of what relationship between these resistors? I am looking for a electronic equation. I'm not looking for a formula. I'm just looking for an electronic equation that shows their relationship. So how would I write that, Yusuf? How would I write that?
1K ohms.
Let's start with just the letters instead of the
Okay,
numbers.
you want R1
Okay, R1
in parallel?
in parallel. How do I write in parallel?
Very two long, slightly diagonal lines.
No, actually, they're meant to be vertical.
Dang.
I'm sorry, if they're diagonal, it's because I'm writing at an angle to the desk. But they're meant to be vertical. So R1, and this means in parallel to, what do I write here?
R2
R2, okay. Then what else?
in parallel again.
In parallel again
R3.
with R3. Is everybody okay with the RT equation? Okay, so this is the RT equation. Now we're going to write the formula. And the RT formula in this particular case if we could have you call that out. Rodrigo, can you call out what the RT formula would look like in reciprocal? 1 over what?
It's 1 over R1
So 1 over R1 there, plus
1 over R2
1 over R2
plus
plus
1 over R3.
1 over R3. How many people agree with this as your reciprocal formula for R total given the circuit that we built? So far, so good? So we start off with an RT equation, which shows their electrical relationship to each other. Then we establish the formula we're going to use. Once you establish the formula you're going to use, now you're going to fill this in with numbers. So this will be, let's use a different color here, 1 over, what do I have here? 1 kilo ohm plus 1 over 5.1 kilo ohm plus 1 over 2 kilo ohm. Does everybody see the reciprocal formula written out? I'm using a slightly different color here. Now we're going to write out the formula for our calculator. What is our keystroke sequence going to look like? Question goes to Jacqueline.
1.
1
Exponent.
exponent.
3.
Okay, so 1 exponent 3.
Reciprocal.
And I'm going to hit my reciprocal key.
Plus.
Plus
1.5.
Okay, and then I will have a 5.1 rather.
5.1.
Yeah, 5.1.
Exponent 3.
Exponent 3.
Reciprocal key.
Reciprocal key.
Plus
And
2.
then do another plus, okay.
Plus 2 exponent key.
2 exponent key.
3
3.
reciprocal.
And we're going to reciprocate that.
Equals.
Equals. So far, so good.
And then reciprocal.
And reciprocal. Exponent.
And equals.
And equals. And probably our engineering at the end, probably.
Almost.
We've been finding out that with the sequence of calculations, we've been needing to hit the engineering at the end. So that being said, this is our keystroke sequence. We've done a lot of practice with this. So I'm now looking for a value. Brad, do you have a value for us, please?
I'm not sure mine's is right, but I got 1.23.
1.23 kilo?
Yeah, kilos.
Okay, and I'll tell you what you can think about here, because if you end up with an R total that is not smaller than the lowest ohmic value, and the lowest ohmic value is 1 kilo, if you end up with something that is not smaller than this, it's wrong. Okay? So that's a dead giveaway, because your parallel circuits happen to be such that your R total will always calculate to be less than the lowest ohmic branch, and the smallest ohmic branch here in this case is 1 kilo. So let's go ahead and do this and not do this too quickly on the calculator, but let's go ahead and do this carefully. So let's clear, and let's go ahead, and the keystroke sequence was 1 exponent 3, there's your 1 kilo, and then you hit your exponent, reciprocal key there, and you hit the plus. Did that complete the first line right there? 1 exponent 3 reciprocal plus. Then what's my next line? The next line is 5.1, so 5.1 exponent 3. After the exponent 3, what do? Reciprocal plus. So here's my reciprocal key, and I hit plus. Then what's the next thing that I do according to the handout? 2 exponent 3 reciprocal equals. So here's my 2 exponent 3 reciprocal, then hit equals. Then the very last thing we do is reciprocal equals and engineering. So let's go reciprocal equals and engineering. And what do we end up with? Oops, I think I pressed it too many times. Engineering, there we go. So we should end up with what value question goes to Yusuf? What do you have?
I rounded it up to get 589.6 ohms.
589.6 ohms. And if you look at the calculator display very carefully, it's 589.595, right? So that third digit is 5 and up, which tells you you have to round the second digit from a 0.59 to become what? 0.60. So the answer we would write down on paper would be 589.60 ohms. So 589.60 ohms. That is your targeted RT rather. Yes?
0 is always necessary.
No, it's not required as long as you are satisfied that that rounded off to be a 0.6. Okay? All right, good question. Is everybody okay with the total being 589.60 ohms? Now we're going to verify that using our multimeter. So the scale we'll leave on 2 kilo, and I'm going to go ahead and put the red probe here and the black probe here. And lo and behold, we're going to end up with 586 ohms. Is that pretty close to my 589.6? Pretty darn close. 585 ohms is what this stabilizes at. I had a question for you. Question goes to Robert. Would it make a difference? What difference would it be if I switch my black probe and my red probe? In other words, suppose I put my black probe at the top and my red probe at the bottom. Would I have the same amount of ohms? Would I have the negative version of this amount of ohms? What do you think would happen if I switch my red and my black probes with respect to the reading on the multimeter?
Yeah, so you'd have the same amount, but it would be negative.
Would it be negative? Okay. How many people would agree that it might be negative? Yusuf, do you agree that it would be negative?
I think it's worth noting that the voltmeter has its own like internal voltage, right?
The voltmeter has its own battery source, yes.
And it's using that to test the ohmic resistance for us. So even if you switch them, is that right?
So if I switch the probes, what do you think would happen?
We're still going to have a positive resistance value.
We're still going to have a positive resistance value. So we have 1 vote for this being negative because I'm switching the probes, and we have 1 vote for them being positive. Who isn't sure? Everybody is sure? Oh, okay.
I'm
all
pretty
right.
sure I'm right.
All right, we'll find out in a moment. I'm going to switch the red probe and the black probe. Now the black probe will be on top, and the red probe will be on the bottom. And lo and behold, let's see, moment of truth. Boom. 585 ohms. Do I see a positive or negative in front of that decimal number? There's no sign, which means it's positive. So I won't get a negative ohms, okay? Because you got to keep in mind, resistance has no polarity. Please write that down in your notebooks. Resistance has no polarity. Resistance has no polarity. It doesn't matter which way I measure resistance, whether I measure with the red probe on top, black probe on the bottom, or I switch it around. Ohms is ohms is ohms. The polarity only matters when I'm measuring voltage and when I'm measuring current. When I'm measuring voltage, you clearly saw in Monday's lecture, yeah, we better reconcile negative voltages when we see they calculate to be negative. But when it comes to ohms, just as a reminder, there is no polarity to ohms. So there will be no negative ohms when I have the probes, black probe at the top, red probe at the bottom. Are we clear on that? That's another reminder point. Be sure to add that to your journals so that when you see a test, you can feel confident that resistance has no polarity. Now, we're about ready to do the next thing because we have a valid value of ohms. So I'm going to show you the next thing that we're going to do, and that is we're going to show you this. It's called current, a current calculation. Let's do a current calculation. Calculation, A-T-I-O-N. And this is very simple. We will do a simple VIR. So we have a V, we have an I, we have an R, and we happen to have 3 resistors. So I'm going to make 4 rows, yes? So I will have an R1, I will have an R2, R3, and totals, yes? All right, we have R values, and the R values were given as 1 kilo ohm, were given as 5.1 kilo ohms, and was given as 2 kilo ohms, and we have a total volts of 5 volts because we're going to use our little 5-volt power supply, okay? So we're going to start our VIR chart this way. Boom. As we've solved VIR charts before, off the meter, as we solved VIR charts before, we're going to engage Ohm's law to help us fill in this chart, V, I, and R, okay? So if we're going to engage Ohm's law to fill in this chart, Ohm's law says we have to have 2 quantities in order to calculate the third quantity, yeah? In the first row, I don't have that. In the second row, I don't have that. In the third row, I don't have that. Look in the fourth row, I don't have that. Only have 1 quantity in each of these rows. Where should I begin? Where should I begin? Rodrigo, where do you think I should begin?
With the R totals.
With R total, because we've already decided from before that these guys were in parallel with each other. From their parallel relationship, we determined our total using the reciprocal formula to be 589.6, and we measured something very close to this. We measured 586 ohms on my board. So we can go ahead and use this value right here, 589.6 ohms, because we calculated that earlier from the previous worksheet. So we fill that in. Very good. That would be an excellent first step. Now, what we ought to do, because everything else hinges upon this value being correct, what we ought to do is probably recalculate this sequence, make sure you feel really good about this being total. Only after you recalculate, which only should take a few seconds to do, you should then, with confidence, be able to say, yes, my total is going to be 589.6 ohms, and I have recalculated and check, check, we're happy. What would be our logical next step for us to do, Wei Ji?
We calculate the total current.
We cannot calculate here because we don't have the voltage. We don't have here or here. But do we have enough information on the 4th row to be able to calculate this current based on Ohm's law?
Yes.
So if we're looking for I, we cover up I with our finger and we see what relationship left in our circle formula.
Or the voltage over resistance.
Okay, so we now have a voltage of this value. We have a resistance of this value. So everybody please take 5 volts right now and divide by 589.6 ohms. And I will do that with you. Turn on the calculator would be a good idea, Co. All right. So 5 divide by 589.6 ohms. And before I hit the equal button, let me ask that value from Jacqueline. What do you calculate for current, please?
8.48 milliamps.
Aha. How many people agree with 8.48 milliamps? Raise your hands. Very good. 8.48 milliamps. Now, because we're going to be using this number for future calculations, maybe we should double check this number. Could we take 5 and divide by 589.6 and reconfirm this and put a double check mark if you feel good about this? Let's try that. Let's clear the calculator, see how long. It doesn't take very long. 5 divide by 589.6, and then hit equals. And didn't have to hit engineering because this started off with a 10 power of -3, so 8.48 milliamps. So have we confirmed this by calculating this a second time? So far, so good? So far, so good. Now, what would be the logical next step for us to do? Question goes to Jacqueline. What would be the logical next step for us to do? What do you think here?
Aren't parallel circuits current dividers?
Okay.
So
So she
I'm
asks a question. I like
pretty
that. When I ask a question, she asks me a question. And aren't parallel circuits current dividers? And the answer to her question is yes. Parallel circuits are, in fact, current dividers.
So we can fill in our voltage with 5 volts.
We can fill in our voltage with 5 volts. What tells us we can fill in our voltage with 5 volts? Where does that come from?
The sheet that you gave us.
The sheet that I gave us. Wow. Well, hey, let me just put this back up here so we can see the sheet that I gave you. Thank you, Jacqueline, for reminding us. And take a look at item number 3 for parallel circuits. Item number 1, she reminded us that parallel circuits divide current. She reminded us that parallel circuits are current dividers. Item number 3, Jacqueline says the voltage is the same across all branches of a parallel circuit. And if you look at the circuit, here's the voltage source. Isn't the top of the voltage source hooked up across all 3 resistors? Isn't the bottom of this voltage source hooked up across the bottom of all 3 resistors? So that means however I measure the voltage across any one resistor, it's the same as connecting the probes directly to the top and bottom of my voltage source. So the voltage is the same across all branches of a parallel circuit. That statement and the formula right here, take a look at number 4, V total is equal to VR1, is equal to VR2, is equal to VR3. Those 2 statements allow us to do this. Parallel circuits are bonehead easy. They're all 5 volts in this particular case. Without having to calculate anything, if you're given the voltage source and they're all in parallel, we can fill in that column. Woohoo! Why? Because of these reminder statements. Voltage is the same across all branches of a parallel circuit, and V total is equal to VR1, equal to VR2, equal to VR3. That's what allows us to fill in this entire column. Good job, Jacqueline. If we're happy with that, now we have one more column to fill in. How do I fill in this column? Ohm's law. So on the first row, if I'm looking for current, do I have enough information according to Ohm's law? If I cover up the I, my current is calculated as a V over R. Do I have a V? Do I have an R? And if I take this V, divide by this R, I should calculate a current. And without having to put this in your calculator, what is 5 divided by 1? 5 divided by 1 is going to give you a 5. What is a whole divided by 1,000? This is 5 whole volts divided by 1,000 ohms. So what is a whole divided by 1,000? This would turn out to be milliamps. 5 divided by a 5 divided by a 1 exponent 3 will become 5 exponent negative 3. Prove it to yourself. Watch this. 5 divide by 1 exponent 3. Is that 5 divided by 1 kilo? And the moment I hit X equals, does it not give me 5 milliamps? Okay, so we filled in the first one. All right, now I'm looking for a value of current for the second one. So somebody take 5 divided by 5.1 kilo. And if we go ahead and do that, Robert, go ahead and take 5 on your, clear. So take 5 and now divide by 5.1. Don't forget your exponent 3. Okay, so there's your 5 divided by 5.1 exponent 3. You put that into your calculator hit equals, hit engineering. What do you calculate?
980.39 micro amps.
Good job. Everybody agree? That's not milliamps anymore, my friends. That is microamps. There's a 10 power negative 6 there. 980.39 microamps. So let's write that down, 980.39, and you write that like a cursive U, capital A. Is everybody okay with that so far? Cool. One more calculation to make. Brad, we have 5 volts divided by 2 kilo. What do we have? 5 divided by 2 kilo. 5 divided by 2 exponent 3. What do you calculate? Something close to 2.5.
Yeah, I got 2.5 kilo.
Is it what power of 10 do you see on your calculator? Is positive 3 or negative 3?
Well, on mine it says positive 3.
Well, okay, then this is what you didn't do. Watch this. Watch this. 5 divided by 2 exponent 3. That's what you needed to key into your calculator. So recalculate. 5 divided by 2 exponent 3. Then hit equals. Now tell me what you got.
Oh, I got 2.5 milliamps.
Milliamps, precisely. That's correct now, okay? And that's, again, this is a learning experience. We're learning our tool. We're learning how to process this information. All right, we now have target currents. Now, this is all built. I have my 5-volt power supply, which I'm going to put right over here. And I'm going to power this 5-volt power supply with my USB cable, which is right over here. Turn this puppy on, and it is now on. And cable is all torquey. Let me see if I can get this cable out to me without it being so torquey. Okay, maybe like so. We'll see what happens. All right, stay. All right, so I expect to see these values of current. And how do I measure these currents? Well, when you're doing current meter measurements, you do something different we haven't done before. Now, I've shown this to you in my PowerPoints. I have current measurement in my week 2 and week 3 PowerPoint. So look at those carefully. Do I have an amp meter scale? Yes. My very first current is expected to be 5 milliamps. Which scale am I going to select to measure 5 milliamps? 200 micro, 2 milli, or 20 milli? 20 milli. So I have to select the scale. I have to go to amps, but before I hook up my meter, I have to decide where I'm going to be measuring the current. Where in here am I going to be measuring the current for the first resistor? I can measure the current at the top, or I can measure the current below the resistor. If I'm going to measure the current above the resistor, I'm going to yank this guy out, right there. And I have a connection point to my power, and I have a connection point. So I have created an open. The open was a jumper wire between here and here. And so if I go put my probe right here, and I put my probe right here on the power rail, am I measuring the current that exists between the power rail and the first resistor? The answer is yes, and we expect, and let's see what we get. Wow, that's pretty close to 5 milliamps, my friends. Very, very close to 5 milliamps. I let go. Now, I'm going to put that jumper wire back, and the jumper wire has to go back to there. I'm going to measure below the resistor. So I'm going to yank out this jumper wire, set it aside, and I'm going to put the red probe at the bottom of the resistor, right there. And I'm going to put my black probe, on my black rail. And in doing so, am I measuring where the jumper wire was to the blue rail? I'm filling in with the ammeter the path of current that was previously flowing through this jumper wire. So from the bottom of this resistor to the blue rail, boom, do I still have my 5.05 milliamps? So does this show that my current above the resistor, my current below the resistor validates my calculation of 5 milliamps? Yeah. What happens if I reverse these leads? Suppose I put the red lead here, my black lead here. Do I still end up with my 5.05? I do. But what do you see on my multimeter? Do you see a negative symbol? Yeah, all that means is that my leads are reversed. That's all that means. My red lead is at the bottom. My red lead, my black lead is in the upper point, and it shows a negative, which is, that just means I have to reverse my leads. So the red lead goes there, black lead goes here, and now it shows me a positive 5.05. Before I can measure my second current, what do I need to do? I have to rebuild the circuit. Okay, now it's rebuilt. And now I'm going to yank out this wire at the top. I'm going to measure the second path. So on this particular path, again, I've broken open the circuit from here, where the jumper wire connected to the top of this resistor, and to the red rail. And do I end up with something very close to my point, my 980.39 microamps? Yeah, I end up with something like 1 milliamp. Is 1 milliamp very close to my 980 micro? Yeah, because 1,000 micro, 1,000 micro is 1 milli. So I'm measuring 1,000 milliamps right now, so that tells me I'm at 1,000 microamps. Close enough. And if I reverse the leads, I'm all tangled here. I'm sorry, I keep twisting this multimeter around. If I reverse the leads and I put the red lead down here and the black lead up here, I end up with the same 0.99 or 1.0, but I show negative. Oops, sorry, move this guy back into view. I show negative on my multimeter, yeah, because my leads are reversed. How do I verify the current on my third wire? Remember, I have to rebuild the circuit so that this guy's back intact. Now I can pull the wire on my third resistor. I expect something close to 2.5 milliamps. Let's see what happens. I am at the top of the resistor, and my red lead is going to be on the red rail, right there. I'm on the red rail, and guess what? Do I have 2.5 milliamps? Yeah, pretty close, 2.54, 2.55 milliamps. How about here on the red rail? Same, it doesn't matter where on the red rail I am. All of this was the red rail that connected current to the third resistor. Now let me hold this in place. Yeah, 2.5 milliamps. Is everybody okay with measuring currents? And if I reverse the leads, put this at this position and this on the red rail, then my 2.5 and a fraction has become negative, yes? All right. So guess what you get to do? You get to build the circuit. You get to reconfirm all of these measurements that we've done according to this video that I will hopefully be able to finish processing this evening and get it out to you no later than tomorrow morning. And keep an eye out on Discord for each other's questions and comments to each other. Keep an eye out for Discord for questions that your classmates may have of me that I will respond to in due course. Are there any questions that you have for me? All right, so is this a pretty good lesson on parallel circuits in terms of calculations between two resistors in parallel, 1 and 2, between 2 and 3, between 1 and 3 resistors, practice on your parallel calculations on the calculator, practice on making measurements of resistances on the board, understanding that resistance has no polarity based on your red and black leads, and also calculating currents, and not only calculating currents and then verifying the voltage is the same across all the resistors, which we haven't done, silly me. One more thing, yeah, I do have to validate the voltages. So we set our multimeter, 20 volts. And we're going to confirm we, in fact, do have 5 volts across each of these resistors. Do I have 5 volts across this resistor, yes or no? Yeah. How about across this resistor, yes or no? Come on, hold tight. Yeah. How about across the third resistor, yes or no? Press firmly. Yeah. So we feeling pretty good? The voltage is the same across the branches of a parallel circuit, yes? All right, so we verified our key points of parallel circuits, which was on this summary sheet. And with that, I will say, bid you a fond good evening. I've got to get ready for my fabrication class, and Mr. Weijie's got to get on the road in a moment. So remember, Weijie, no speeding, no speed tickets. Just get here when you get here. And the rest of you have a marvelous, marvelous weekend, okay? Adios, my friends. Let me do this, get off of the camera.